Alright, so section 3.5, we will discuss a little bit about the property of the uniform plane wave in free space. So in say section 3.5, we'll look at the characteristics of plane wave in free space. In previous section, we considered the current density on the infinite plane current sheet, which can be used to produce uniform plane wave. However, we didn't discuss the time domain function of the current density function. And we assume that any arbitrary function can be applied. And well, that's true. However, in this section, we will in particular look at the solution corresponding to sinusoidal function, which is usually the basis for all electromagnetic wave functions. The sinusoidal, the Fourier transform or the cosine series, which means that any waveform, any arbitrary waveform can be synthesized using summation of sinusoidal signal of different frequencies. So the sinusoidal function is the most important, most common form of periodic signal. And the sinusoidal function can produce continuous or discrete spectrum on the frequency domain. Any non-sinusoidal signal can be synthesized using sinusoidal signals. So it's important to know the response for sinusoidal signal so that response of non-sinusoidal signal can be synthesized with solution for sinusoidal signals. So suppose we replace or we use a sinusoidal signal for the current source. That is, Js is represented with minus of J sub S0 times cosine omega t, Ax. So the function specifies that the current is vibrating on the x direction, and it's a sinusoidal function of cosine omega t. What is the frequency of the function? Omega. Omega is the so-called angular function, which can be represented as omega equals to 2 pi f. So omega is the angular frequency, 角频率。那 f 呢指的就是频率了frequency。So of course cosine omega t is a sinusoidal function, as you already know it. And the J sub S0 stands for the magnitude of the current function. And minus sign just says that the current is going down, going to the negative x direction at t equal to 0. And it's in fact going up and down. And because there's no specification about the position, so you can see that the current only appears at z equal to 0. So the current only appears at 0 position, z equal to 0 position. And according to the specific solution derived from the previous section, we can substitute Js function with the specified sinusoidal function and end up with equations 3.90 A and B for electrical field and the magnetic field. know that the difference between E, H, and J is what? Is the function parameter of E and H are omega t minus beta z, minus or plus beta z, while the function, sinusoidal function for J only have omega t. So the currents only located at z equal to 0, while the wave, the electric and magnetic field, can propagate to positive and negative z direction and fill the whole space. So as you can see, equation 3.90a and b are specified for every place, every time, any time instant, and for any time instant for t and any position. The E and H field are specified. They are corresponding to eta sub 0 Js 0 over 2. Why there is a 2 over here? Because half of the field goes to the positive z direction, the other half goes to the negative z direction. And you see the difference or the ratio between E and H is eta sub 0, the intrinsic impedance. And parameter, function parameter is omega t minus plus beta z, where the top one stands for the components going to the positive z direction, and the second one, the plus one, stands for the component going to the negative z direction. And in this function, we have another parameter, that is beta z. So what is beta? Beta is defined as wave number, 是吗？好了，贝塔其实有好多名字哦。OK， 我刚刚讲 wave number 啊，是其中一个名字了。不过我们课本上叫做相位常数。So beta is specified as phase constant. Phase constant. And it's related to angular frequency and the velocity. So you can remember this relation. We are recommended to remember this relationship, but you don't necessarily have to memorize this, but you are encouraged to do so, all right? 2 pi over lambda. Okay. Okay. So omega is the angular frequency. Vp is the phase velocity. Phase velocity of the wave. 2 pi is radian. 2 pi radian. Lambda is what? Wavelength. 波长. Okay. So beta is phase constant. Lambda is the wavelength. And so these two equations represent sinusoidal time-varying uniplane wave propagating away from the current sheet. So as we already know, there is a current going up and down in the middle of the classroom, that is at the z equal to 0. Half of the power goes to the front and the other half goes to the back. And as you can see, electrical field is vibrating on the x direction, and the magnetic field is vibrating on the y direction. So H is the horizontal one, and E is the vertical one. And because the sinusoidal function cosine can have either positive or negative value, so you can see the electrical field intensity is going up and down, and the magnetic field intensity is going to the front and back. And know that the Rosen square rule still holds. So E cross H will give you the propagating direction. And that's part of the reason why there is a difference at the Z greater or smaller than 0 in magnetic field intensity. Because you need to invert the H direction so that the propagation direction on this side is going to the left. And in this side is going to the front. And in this picture, in this plot, I deliberately draw the current direction as the blue arrow and the corresponding electrical field direction as the red arrow. Do you notice that they are of opposite direction? 有没有看到？在电流源处这一个 moment 这一个当下，它的电流方向跟它的所产生所对应的电场方向是相反的。为什么？当然在事实上面可以看得出这一点，但是从物理上你要去怎么样理解这件事？每次定律有没有想起来？因为你的电场的产生其实是为了对抗你的时变讯号。我们这边的时变讯号是电流所以你知道电磁波的产生就是为反对而反对所以它的电场的产生方向跟它的电流强迫，电流是讯号源强迫给的，而电场是感应产生的，而它感应的机制是对抗现状的变化，为反对而反对所以你会看到的事情是，你所产生的电场方向其实是电场方向跟电流方向是平行的，但是它们是相反方向。简单讲就是冷次定律 ，OK？ 好。那电场方向既然决定了，那电流方向、磁场方向也可以决定，因为你的传播方向是已知的嘛，你知道它是要往左往右去传播 ，OK？ 那你会看到这个抖动是什么？这个正弦波的抖动就是对应你的讯号源的电流的正弦波变化了那我们刚刚有提到一件事情，就是电磁场的讯号是有时间延迟的，也就是说，你在这个地方所灌到的电场跟磁场是什么时候产生的？是之前产生的，之前的那个电流所产生的所以这个地方往下的电场其实对应到之前往上的电流所产生的所以越前面的那个电磁场呢，表示什么？越早所产生的那个越早出现的电流所产生的，好吗？So here another two illustration. So you can see that as the time progress, the electrical current in the middle varies. So for t equal to 0, the current magnitude reaches the maximum, and the direction is pointing down. At t equals to lambda over a, it still points down, but the magnitude is reduced. At t equal to lambda over 4, which is corresponding to 90 degrees, now that for cosine function at 90 degrees, the value is 0. So you can see that at the source position, the current density at the present, that is t equal to lambda over 4, is 0. So there is no currents in this on the current sheet. What happens if the time keeps going? For a time greater than lambda over 4, the direction of the current will become upward. So you see the current is going up and down in the middle, and the corresponding electric and magnetic field also goes up and down or front and back as the time progresses. Alright, so we shall now discuss in detail several important parameters and properties associated with the sinusoidal function. So the first important thing is the argument of the function. As you can see, the argument is made up as omega t minus or plus beta z of the cosine function. And this in the process is actually the phase of the field. The phase of the field, which can be represented as parameter phi. Phi equals to omega t minus plus beta z. Note that one important thing about propagating wave is the argument, the parameter of the function, must comprise description about time and space together. 所以对于波动方程式的解来说，假如你的这个场要在空间中传播，它就必须要同时包含它的那个函数里头，它的场的那个function场的函数里头，就要它的 argument 它的参数就必须要同时包含空间跟时间的描述。这个概念很重要，不然我不会转到 Mandarin 来跟你再强调一遍了。你的 argument，the argument involving the function for propagating wave must comprise description about time and space simultaneously. You need to comprise. So as you can see here in 3.92, the argument phi, the phase of the function of the sinusoidal function equals to omega t minus and plus beta z. So it comprises description for time and space simultaneously. Okay? Okay, the second observation is if you taken the derivative of the phase, that is del phi over del t. You've taken the derivative, time derivative of the argument. You end up with omega. That is the angular frequency. 角频率 angular frequency. And the implication of angular frequency is the rate of change of phase with time for a fixed value of z. So at a fixed observation point, as the time progresses, you count the change of phase, you calculate the change of phase, then the value is omega, is the angular frequency. So this is the frequency for a fixed time period, say 1 second. Is the variation in radian is omega. And if you divide omega by 2 pi, you will give you frequency. That is how many 360-degree change for every second. 每秒每单位时间的波的变化次数所谓的波的变化次数，也就是360度的相位变化或者是2 pi radian 的相位变化所以这边要去看到的是，你把 phi 对时间微分得到的是 omega 等于2 pi f 所以频率就是在特定的观察点上，在单位时间内所看到相位变化周期的次数了So that's the frequency. Frequency f is the number of times the phase changes by 360 degrees in 1 second for a fixed position of z. And next is the derivative of phi with respect to z. So you perform a special differentiation. If you perform a spatial differentiation over the argument phi, you end up with positive or negative beta. That is the so-called phase constant. So this is the magnitude of the rate of change of phase with distance z for a fixed value of time for beta. The situation is pertinent to taking a still photograph. So if you take a picture of the propagating wave in the space, you can calculate for a specific distance, say 1 meter, how many 360 degree phase variation appears in 1 meter. 也就是在单位长度底下，你有看到几个周期性的相位变化，360度的相位变化。那这一个次数就称之为贝塔称之为你的相常数称之为你的相常数。So so beta is defined as 2 pi over lambda, as we see here. Beta is defined as 2 pi over lambda. And what is lambda? Lambda is the wavelength, is the distance for the signal to vary 360 degree. 所以波长是特定相位间的间隔，比如说这一个正弦波它的最高点或最低点或者 zero crossing 点的间隔就是一个波长那 zero crossing 的话要小心这个是由大变小的 zero crossing， 这是由小变大的 zero crossing， 所以我们在算的时候要同一个形式的 zero crossing 才是对应到一个波长一个360度的相位变化 ，OK 所以这边几个基本关系啦 ，lambda 的 beta equals to 2 pi over lambda or omega equals to 2 pi times f. You should try to memorize this basic fundamental relationship. Okay, and as you can see from this relationship, VP can be determined by omega over beta, which is not that familiar to you, but if you further decompose it, if you take a further look at the definition of omega and beta, you see that omega can be represented as 2 pi times f, and beta can be represented as 2 pi over lambda. Then this thing becomes f times lambda, which is the more conventional or more common representation for the propagation speed. V equals to frequency to the product of frequency and wavelengths. V equal to f times lambda. So and here Vp refers as to the phase velocity. There are some subtle differences between propagation velocity, phase velocity, or group velocity. So in fact, in electromagnetics, the velocity can be the so-called phase velocity, propagation velocity, group velocity, blah, 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 blah. But for the meantime, phase velocity is easier to understand. It's simply just the product of frequency and wavelengths, and you can also memorize as 1 over square root of mu times epsilon, based on the median property, electromagnetic property of the median to determine the velocity of phase. So let me discuss a little bit more about the velocity of, well, VP0 should stand for the electromagnetic wave velocity in free space, which can be 3 times 10 to the 8th. Is this the largest value that you can have for speed for electromagnetic wave? Well, yes and no. Okay. Let me begin with let me explain it as the answer is yes. Okay. Effectively, the highest velocity that you can have with this electromagnetic wave is 3 times 10 to the 8th, because epsilon and mu are nearly minimum in free space. 好了，简单讲啊，因为真空中的介链系数跟介磁系数几乎是最小值的，但你听我这样讲就知道它不是最小值啊。事实上，一般物质的那个介磁系数是比真空的介磁系数还要小一点点。大概差个1/1000吧，原因是大部分的物质是所谓的反磁性物质，但这个东西不是那么的重要了哈，你大概稍微知道一下，就是说一般的非磁性物质，其实它是带有1咪咪的反磁性，所以它的介磁系数其实是小于μ0的，但没有差很多。但大部分的材料的 epsilon 都大于真空，都大于真空epsilon 0是8.864乘上10^-12次方，大部分材料都大于这个 epsilon 0事实上我们比较常用的是 epsilon r， 叫做 relative permittivity， 或者有的时候叫做 dielectric constant 那它就是一个对于一般物质来讲，它是一个大于1的数但是对于大部分的物质来讲，它的那个 epsilon r 值其实也没有变动范围没有很大。例如说，空气跟真空的 epsilon r 就等于1嘛，空气差不多也等于1。基本上那个 epsilon r 值跟那个比重比较有关，所以你像保丽龙这种轻飘飘的东西，它的 epsilon 值 r 值也差不多等于1。那一般你手上摸到的、拿到的塑胶它的 epsilon r 值大概介于2到4。然后假如是石头的话，大概是石头类啦，石头陶瓷大概是4到10之间吧。那像是那个你的眼镜的镜片因为它是 polymer 材质的，其实塑胶啦所以它的 permittivity 大概是4左右那钻石有什么特别特性？钻石的一个特别特性就是在所有透明的材质里头，它的介链系数最高。从电池的角度来讲，钻石的特性是它是所有透明材质里头介链系数最高的一个材料，所以它的折射角最大。所以你把钻石拿去经过一些几何形状的打磨之后，那个光就会在里头弹来弹去。它大部分的光会被锁在钻石里头，但是它多多少少会散出去。那透过那些切割让它尽量在钻石里头产生全反射。那么你的那个打进钻石的光呢，就会往四面八方散出去。所以你到珠宝店的时候如果我是男生，我不去看珠宝店不要到时候你女朋友会压着你去的OK 你就会看到那个他们珠宝店一定会有那个强的那个聚光灯嘛，对不对所以它展示的时候，你会看到那个钻石在里面闪闪发光但是不要买钻石买钻石不保值因为现在人工合成技术，它可以合成出来，把那个碳压一压它的那个介链系数会比天然钻石还要来得高1咪咪OK， 所以 你可以跟女朋友讲说，你买黄金好了，不要买钻石哦，因为黄金是那个宇宙初期里头好大好大的星星爆炸时候死掉的尸体了哈。未来已经在宇宙中再也生不出，不太容易再挤出黄金来了哈，不太容易再炼出黄金了哈。OK， 好。后来so let's move on. So if you taken the differentiation of the phase constant, you end up with omega times dt minus plus beta times dz. And you massage the equation a little bit, you get dz over dt, which equals to omega over beta. That is the phase velocity. So as you can see here, this is the phase velocity is determined by the angular frequency and the phase constant, beta. And for free space, the phase velocity of free space is 3 times 10 to the 8th. And which, as I already demonstrated, as already shown, that Vp can be, with some change of variable, it can be replaced with lambda times f. That is the velocity of electromagnetic wave. And here is, in the next slide, is the name for frequency band that is commonly used. So for M radio, it's in the region of a little bit greater and smaller than 1 megahertz, which is about 500 to 1600 kilohertz. Frequency modulated radio FM is assigned as 88 to 108 megahertz, which is also referred as the VHF band. And as I already mentioned, that the microwave oven operates at 2450 megahertz, 2.45 gigahertz. And radars usually operates at 10 or 24 gigahertz. So here is the name and the corresponding frequency band and the wavelengths for commonly seen microwave bands. So you can look it up yourself. And here's another table for frequency range and the band name. For me, it's more, we commonly use these names for microwave bands. Now we may discuss later about whether, well, it looks illogical. These names look illogical. It's kind of difficult to memorize these band names. And this was done on purpose because these names are assigned during the period of the Second World War. So these names are named to confuse the German. Alright? So they are named so that the Germans do not understand what the Americans speak about. So it's quite natural that you can find any logic between these names. 因为那年的时候是2战的时代了所以它的那个名称其实没有什么逻辑性了但是只是后来习惯成自然了我们做微波的大家也都是用这些名称的So the last two things we like to mention is the intrinsic impedance. As already mentioned, it's intrinsic impedance is not a resistance. It's actually the ratio of E and H field. For free space, for wave in free space, the ratio is 377 ohm or 120 pi. Okay, so that is the ratio of electric and magnetic field in free space. And the last thing I'd like to mention is the direction of wave propagation can be found using the right-hand screw. So the direction, if you cross the electrical field direction toward the magnetic field direction, you will end up with the propagating direction. So if E is in the x direction, H is in the y direction, then the product, cross product of E cross H is in the z direction. All right? So here you can see at this position, E field on the two sides are pointing up. H field is pointing to the front and back across the current sheet. Then the cross product of the E and H field in front or in the back of the current sheet is pointing to the right and pointing to the left, as represented as the green arrows. And so here is finally is example 3.11. That is an example for the electrical field. So here is the electrical field representation, a little bit more complicated. You see it has two components, X components and Y components. Well, that's legal. That's legal. But you can see the argument are the same. 3 pi times 10 to the eighth times t minus pi beta minus pi z. So you can identify the parameter omega as 3 pi times 10 to the eighth, and the phase constant is pi, as you can see here. And what is the frequency? Frequency F equals to omega divided by 2 pi, so it's actually 1.5 times 10 to the eighth. And what is lambda? Lambda is beta over 2 pi over beta. So the wavelength lambda of this case is what? 0.5. 0.5. So the frequency is 1.5 times 10 to the eighth, and the wavelength is 0.5. yeah, here is the result. 频率是1.5乘以10的8次方，波长是对不起，我算错了 ，OK， 波长是2啦，2公尺了所以它事实上是150 MHz 150 MHz 的波长是2公尺，所以你把它两个乘起来还是3乘以10的8次方And part B is the derivation of the magnetic field, which can be done by taking the cross product of the propagation direction, which is AZ in this case. AZ cross E divided by eta will give you the expression for the magnetic field. So you can look at this problem, or be sure to look at this problem at home. All right.